Okay, another example, submerging a balloon. So we have a sturdy balloon. Okay, let's say I assume it's like a perfect sphere here, all right? And the volume of that balloon is 0.5 meters cubed. And attached to that balloon is, I guess, a piece of iron, right? I'm trying to make it look, I guess, three-dimensional here. So this is my iron in here. And that piece of iron has a mass of, well, 2,250 kilograms, 2.5 to the power 2. It's attached to this iron weight, tossed overboard into a fresh lake. So we need to put that all into the water. So it's initially tossed in the water, and we're told that the balloon, here's the balloon in the water, and it has a pressure of, well, an atmospheric pressure. So I'm just going to say it's 1.01 to the power of 5 pascals. Of course, initially it doesn't move, and so they have to have a skin diver that drags it down deep enough that it'll just remain submerged. Okay, so find the volume of the balloon at the point where the system will remain submerged in equilibrium. So I guess since we see this word equilibrium, my thinking is we should probably draw a free body diagram for the balloon, right? So we have forces that are acting on the, and I'm going to be looking at the balloon and iron system. So we have a upward force, which is our buoyant force, and then we have a downward force, which is the weight of the balloon and the weight of the iron, which is predominantly what it is. And these two forces are equal to each other, right? Forces are in equilibrium, so the buoyant force is equal to the weight. Okay, so the buoyant force is really composed of two buoyant forces. We have the buoyant force from the balloon, and we have the buoyant force from the iron. Okay, and then similarly we have the weight of the balloon pushing downwards, and then we have the weight of the iron going down. And remember, hopefully, from we just finished the unit on buoyancy, so the buoyant force is equal to rho of the fluid, okay, which would be just, I guess we should write that down. The density of the fluid is just, I assume, just lake water, which is 1,000 kilograms per meter cube, right, times the volume that is displaced, which would be the volume of the sphere or the volume of the iron, multiplied by g. So let's go ahead and replace those in here. So we have the density of water multiplied by the volume of the balloon. I'll just call that B, the balloon, and then G, plus the density of the fluid times the volume of the iron. I guess I'll just use Fe for iron, and then times G. And then we have the mass of the balloon times G, and then the mass of the iron times G. And you can see that, well, it doesn't really, guess what, all these G's will cancel out, right? So we don't have to use that at all. And so now what do we do? All right, we have, let's see here. Well, we know the volume of what? We're told that it has a volume of 0.5 meters cubed. Is that the volume that it has right now? I mean, I guess it's under the water and it's compressed, right? So we can't assume that the balloon has the same volume that it did when it was outside of it, or can we? Let's see here. Well, no, because I'm actually trying to find that in the end, right? So the volume of the balloon, right? If we put that all by itself, this expression, we'll have the mass of the balloon minus the mass of the iron, right? And then minus the density of the fluid times the volume of the iron, and then all of that divided by the density of the fluid. Okay, so we just need to now figure out stuff. What do we know? We know the density of the fluid, which is 1,000. We need to figure out a couple things. We need to figure out, let's see here, we need to figure out the mass of the balloon, and we need to figure out the mass of the iron. All right, now we do know the mass of the iron is 250, so we know that. I see that. We also need to find this volume of the iron. We need to figure that out. All right, so let's do some things on the side here. Okay, maybe we'll erase this bit here. So the volume of the iron, right? What is that equal to? Remember, density equals mass over volume. And we need to look up, I guess, the density of iron, right? In order to find the volume of the iron if we know the mass of the iron, right? So let's look that up. I'll go find it on the internet right now. And it turns out that the density of iron is 7.86 to the power of 3 kilograms per meter cubed. That would have been nice if that was provided in the question. Okay, so the volume of the iron would be the mass of the iron divided by the density of the iron. So that would be 250 kilograms divided by 7.86 to the power of 3 kilograms per meter cubed. So this should give me the volume of the iron, which works out to 0.0318 meters cubed. Okay, looks like I'm going to need a lot of space just to do part A. Wow. Okay, anyway, let's continue. I need to then, so I've got that, got the mass of the iron, mass of the balloon. Oh, I don't know the mass of the balloon. So I'm guessing I'm going to use a similar expression. What is the mass of the balloon? Well, the mass of the balloon would be the density of the balloon, all right, multiplied by the volume of the balloon. All right, now we do know the volume of the balloon is 0.5. So what is the mass of the balloon? So I'm guessing we're neglecting the weight of the material, and we're really just finding, when I say the mass of the balloon, I'm looking at the mass of the air that's inside of the balloon. So you need to look up also the density of air, which turns out to be 1.29 kilograms per meter cubed. So the mass of the balloon's air, as I should say, is 1.29 multiplied by 0.5. Okay, this is in kilograms per meter cube, and multiplied by 0.5 meters cubed, which gives me 0.645 kilograms. Okay, so this is really a fluids problem. So now we just have to plug away in here, and we have the mass of the balloon that we just recorded, 0.645, the mass of the iron, which is 250, and then we have, that doesn't make sense now that I look at it. Anyway, I'll continue. Then 1,000, and then multiplied by the volume of the iron, which is 0.0318. And then that's all divided by 1,000. Now, I see an error because I'm going to have a negative number here. And that doesn't make sense, but that's okay. First time I'm doing this. I do realize that when I was solving for volume here, I have mass plus mass. So this should be a plus here. This should be a plus here. There you go. And working it all out, we get a volume of 0.2188 meters cubed, okay, which is 0.219 meters cubed. And that was just part A. My God. All right, let's go on to part B. Find the balloon's pressure. So this was actually just a whole buoyancy problem, and I'm running out of space. So I'm just going to record this answer somewhere here and come back to it. Okay, there's my answer. And now in part B, okay, I'm looking for what is the pressure at that point. Okay, so this must be related to the ideal gas law, right? We haven't used that yet. PV equals nRT. We just found out the volume. We're looking for the pressure. So the pressure would be nRT all over the volume. So we've got the volume. Do we know what the temperature is of the gas? No. And I don't know the number of moles either, so it's not going to work out by just doing it that way, right? So maybe we think about it as, oh, this is the final volume, and we knew that the container had an initial volume of 0.5 meters cubed. We knew that initially the container was, I thought it said that somewhere, atmospheric pressure, yeah. So the initial pressure was 1.01 to the power of 5 pascals. Right? So, and I bet we're making an assumption that the water doesn't change in temperature. Otherwise I can't solve it. Oh yes, constant temperature, right? So what you're going to use is, right, P initial, V initial, all over in, and then P final, V final, and RT. And you can see, it's just really Boyle's law. The number of moles, the temperature, gas constant all cancel out because they're constant. And so really it's just a Boyle's law problem. So our final pressure is what we're looking for. Our final pressure would be equal to the initial pressure times the initial volume divided by my final volume. So that would be 1.01 to the power of 5 pascals. The initial volume is 0.5 meters cubed, and the final volume is 0.2188 meters cubed. So our pressure is 2.31 times 10 to the power of 5 pascals, I think, yeah. Okay, so now we use the ideal gas law. Then last part, C, what is the depth, right? And so, back to fluids again, right? Because we're assuming that when you go in the fluid here, right? Let's say this is my water in here, right? And then I have my balloon down here, right? Okay, let's put some water all around it, right? And there is you go down that depth and it will have some kind of pressure at that point, right? And we just determined that, right? That's that final pressure of 2.31. So if you recall from the earlier chapter on fluids, pressure is equal to pressure initially outside out here, which is just an atmospheric pressure, right? Plus rho g h, right? And we're solving for h. So the final pressure was 2.31 to the power of 5. The pressure outside at the surface of the water we'll assume is atmospheric pressure, 1.01 to the power of 5, plus the density of water, which is 1,000, times g, which is 9.8, times h. Okay? And so then our height, when you work it all out in your calculator, is 13.2 meters. So that is the depth that skin diver had brought the balloon down to. Okay, rather long problem. Hopefully this makes sense. This is a really, I would say, a better question to put on an exam because it's kind of hitting both fluids and ideal gas law at the same time. Okay, that's it.